Hi everyone. Today I'll be presenting my computational photography project on low-cost laser line triangulation detection for relative planar surface depths. So the motivation of the problem is I wanted to detect millimeter level surface deformations on large planar structures such as aircraft fuselages, which may be dinged up by burst strikes or hailstones, and wing surface deformations on an aircraft wing, such as on the right. The challenge is the commercial lidars only have centimeter precision above a meter away, and they're quite expensive. As you can see, I've showcased two lidar scans from the Ouster and the Regal lidar, and each point cloud dot is of centimeter precision, and you cannot visually tell where the millimeters of normalities exist. And I propose a triangulation-based setup, which is cost-effective and very accurate. So the setup is as follows. We have a camera and we have a laser line that projects a line onto the surface. And this line will have a slight pivot at the deformation that is present on the relatively planar surface. And if we can detect this pivot, we should be able to detect these abnormalities that are millimeter level on the planar surface. So to formally define it, we have a camera and a laser line projector at a distance b. The camera is away from the plane at distance z, and the deformation on the planar surface is of size delta z. So we know dz equal to fpx into b upon z by the perspective camera projections, and if we take the perspective camera projection at distance z and distance z plus delta z and subtract it, we find that the pixel deviation at this dent or abnormality will be proportional to the focal length, the baseline, delta z, which is the size of the abnormality, and inversely proportional to z squared. One key point about the setup is we do not require calibration of the laser plane or the baseline extrinsic. So this is very useful because the robotics application is very sensitive, and over time the extrinsic calibrations tend to degrade. Also, since we do not rely upon precise calibration and only proportionality, it is very robust to different environmental conditions. So our rig setup is as follows. We have the laser line projector on the right at a distance b. We have a camera, and we take an image of the laser line, and we try to find the deformation on the laser line. So moving on to some theoretical aspects, at 2 meters away, we're able to detect 2.5 millimeter abnormalities on the planar surface because 2.5 millimeter abnormalities leads to a 1.1 pixel deviation, and we need at least 1 pixel deviation to detect these abnormalities. So the key idea is you take the laser line, which may be slightly curved because of the deformations on the planar surface, represented by the black line, which is highly exaggerated. You fit the supposed straight line that the laser line would go along, and the straight line is formed by taking the principal component analysis of the laser line pixels and just taking the vector direction along it, and we find the projection of actual laser line pixels and the PCA direction. And the deviation of the projection distance is the relative depth along the 1D line, essentially. So the x-axis is the PCA direction, and the y-axis is how far the laser line pixel is from the PCA vector. So to make the whole setup faster, instead of taking one picture at low exposure, one picture at normal exposure to showcase the abnormalities, we take two pictures, one at low exposure and another at normal exposure. And the normal exposure is used to refer to the abnormalities. And we can match the laser line through epipolar geometric matching. So here is a setup again. You can see on the left, there's two cameras instead of one, and we can just take a video and scan the whole airplane fuselage. So the normal exposed image on the left, the underexposed image on the right. We find the deformation curve. Basically, we find how deviated the laser line pixels are. And each local minima corresponds to the inward abnormality because the laser line is on the right of the camera. And according to the equation we derived before, the minimas will correspond to the inward abnormalities, and the y-axis is essentially the relative depth. We can get the positions of these abnormalities that are inward, such as dens, dings, and troughs. And yeah, so basically, if we project it onto the normal exposure image, we see that like the holes, dents, and these are detected quite reliably from 2 meters away with a low-cost solution. So we collected a data set of 391 dens just to validate our performance. Side of the fuselage of 6 meters cross 0.75 meters, and 330 images over 11 seconds at 30 frames per second were taken. And we were able to get really high recall rate. That is, this method empirically also works. And yeah, low-cost laser triangulation is feasible to detect millimeter scale surface detections. Thank you.